I think statistics is just a mechanism for saying we don't understand. I feel we live life in between pure order and pure chaos, between zero information and maximum information, between pure pattern and static on our TV, between zero entropy and maximum entropy. I think XOR helps us understand this in-between world we live in. I teach a course called Digital Design, and I'm going to take you into the dark corners of it. The course starts off with some binary Boolean discrete math. I like to imagine it as a person P and a person Q arguing with each other. Zero means I think you're lying. One means I think you're telling the truth. The stuff inside these boxes right here represents all the possible outcomes of their arguments. Reality is inside these boxes, and ultimately the reality could be false, or ultimately the reality could be true, or ultimately P could be right, or P could be wrong, or Q could be right, and Q could be wrong, or some crazy combination of these two. There's 16 possibilities. The most interesting one is this one. The course teaches how to build an entire computer out of this NAND gate. After teaching this several years, I'm going, well, maybe I can build a computer out of something else. So I tried next trying to build it out of an AND gate. That didn't work. I tried to build it out of a NOR gate, and it worked. And I tried to build it out of a OR gate, and it failed. These other ones up here and here are trivial. Can't build a computer out of those. This one or this one or this one, because they just look like more complicated versions of these two. But then I began playing around with these XOR gates. XOR gates, this is the symbol for an XOR gate. Right here, the circle with a plus in it. These XOR gates are not mentioned in the digital design course, but they keep cropping up at the very end, the last moment when you build the circuit. They might make it a little bit more simple. But you can't build a computer out of them. I tried. I spent hours trying. This is a XOR. And all you do is you just bounce back and forth between these two. You just oscillate between these two. With these purple ones, I can build everything here. I can do anything I need to logically. Either one of these. And I suspect this one and this one I could too. But these two just bounce back and forth between them. They've got this weird behavior. And that's what I want to talk about. So there's two definitions of XOR that are out there in the electrical computer engineering world. We want to focus on this behavior. When an odd number of inputs are true, then the output's true. When an even number of inputs are true, then the output's false. This is a simulation package where we're building circuits with XOR gates. And you can see here we have to define what the behavior of the XOR gate is. So we're focusing on this odd detector function of an XOR gate. Some of you have perhaps never heard that you can make an entire computer out of a NOR gate. So I just wanted to prove it to you. Here I used a NOR gate to create a NAND gate. But the big question is, what's lost with this exclusive OR? What's it good for? Why does it exist? With this NOR and NAND gate, I can pick up single event upsets, the effects of a nuclear blast or a cosmic ray that needs to be pulled out of the muck of chaos and leveraged by an electrical circuit. But this exclusive OR just bounces back and forth. So it's really only going to be good for things that oscillate, that have patterns. And we're trying to just document those patterns. So I was creating a test for this class called Digital Design, and I was looking through Wikipedia, and I remembered CRCs. So I started reading about them, and I go, wow, they're based upon XOR gates. I totally lost my focus trying to create the test, and I zoomed in on this even odd parity finite state machine right here, this picture. You know, if you're
a 0 and you get a 1, now the total's odd. And if you keep getting zeros, you stay here at odd until you get a 1, you go back here to even. And the math of it looks sort of like long division. You know, we're taking this 11 and dividing it into here in binary style. So if I put a 1 right there, then this turns into 11. So this turns into 11. And 1 XOR 1 is 0. This one sort of hangs around and is going to impact the next time increment or the next bit coming in. The next bit coming in is a 0. So I need to get rid of that 1. So I put another 1 up here and multiply that 1 times that 1. And now I get this one and this one XORing out to 0. And this one's left around, hanging around, impacting what's going to happen. But I really don't need to get rid of it because that and that, if this is the next one that comes in, then that one and that one are going to XOR out to 0. So I don't need to multiply this by 1 anymore. I just need to multiply it by 0, and that 0 hangs around and impacts the next one. So this is the magical divisor. This is the input, and then this is my output right here. So then I started playing around with different kinds of information coming in to see if this finite state machine stayed the same, and it does. So here's our second example right here, and it's staying the same. And then I did a third one right here and it stayed the same. So I'm calling the output right here Z. And it's basically an encryption of this. So we have the states even and odd. Even would be a 0, would be the green right there. Odd would be all these 1s back and forth. Here you can see a bunch of 0s. That's the even state. And here in our output, the 1s are the odd state. But the mysterious thing is, how does an XOR gate create a finite state machine? These states are remembering information. It's memory. We struggle to create memory with a NAND gate. So I went on to a CRC2, and I looked at this and I saw this asymmetrical part right here in the finite state machine. Yeah, I have 2 rows now, so I can have 4 states. There's 2 possibilities with a CRC2. We can put a 0 in the middle there, or we can put a 1 in the middle there. When I put a 0, I got this anomaly, and then when I put a 1 there, I got this perfect symmetry. And so the question was, if I have this anomaly, and there's not just perfect symmetry, then maybe there's a way that I can pick up those single event upsets. So I went on to a CRC3. And then in a CRC3, I got perfect symmetry, even with a 0 there in the middle. Right, so I have 3 rows here of outputs. That means I can have 8 states. And you can count them. And you can start to see there's symmetry here. And I started playing around more and more and more, and all I got was symmetry. All I got was symmetry. CRC4, and I just gave up. It got way too complicated for me to check. But this, man, initially it dawned on me that this just looks like DNA, a DNA sequence up here. And I'm wondering, wow, if I go back to the Genome Project or I go look at biology, can I see any kind of this XOR gate being used to document the DNA sequences? Maybe this can be used to, I don't know, collapse the DNA sequence. Maybe it can be used to capture it in a more concise way. Maybe this will influence how DNA is thought of. So then it's been morphing in my mind. The neural net spiking is associated with these cycles. This could be the secret to downloading our brains. It could inform quantum computing. It could help us document evolution. This is not statistics. I believe we search for clarity. We live in here and we look out towards the clarity, and we look out with XOR gates.